Now we observed that the 0.16 newtons we got here is the force that would have to be exerted directly on the 100-gram mass to accelerate it at 160 centimeters per second squared. Okay, so that would be 0.16 newtons exerted in the direction of motion at the position of the 100-gram mass, the position being 40 centimeters from the axis of rotation. Now, 0.16 newtons exerted out here, where the axis of rotation is here, is equivalent to what force exerted 4 times as close to the axis of rotation? Okay, well, it has the same effect as 4 times the force exerted at that 10 centimeter position. 4 times the force at 1/4 the distance gives you the same rotational effect. There's an energy argument for that through any given well, I don't want to state the whole thing. Through any given angular displacement, you get a certain change in angular kinetic energy and so forth. But it's going to be too many words, so I don't want to go there. Okay, just intuitively, if I want to support this precarious, too precarious. If I want to support this tray full of chalk by exerting a force at this position, let's assume we have some kind of an axle over here behind my body, okay? The force I need to exert to support this is less than the force I would have to exert here. And of course we demonstrated that in class. So if we ignore the weight of the meter stick, if the meter stick has negligible weight, if I exert a force here, okay, I can move this thing and I can accelerate it at a certain rate. If I want to accelerate it at the same rate from a point 4 times as close to the axis, I'm going to need 4 times as much force. And we basically convinced ourselves of that just by pushing things that are constrained to move on a circle. The energy argument and so forth is easy enough to make, and we will make it. But from that we get this definition of what we mean by torque. Torque is R, which is the distance from the axis of rotation out to the object, multiplied by the component of whatever force is exerted out there, the component perpendicular to the vector from this point to this point. Okay, picture might be like this. Okay, we have an axis of rotation here. We apply a force out here at a 40 centimeter distance, then our R vector would be the 40 centimeters from here to here in this direction, and a perpendicular force would be in this direction. If the force wasn't perpendicular, we would use only the component of that force in this direction. We get the same torque by multiplying an R vector of half the magnitude by a force vector of twice the magnitude. Okay, so, or an R vector of 1/4 the magnitude, 4 times as close to the axis, multiplied by 4 times the force, gives us the same torque, the same rotational effect. More formally, we define torque as a cross product of the R vector crossed with the F vector. So if the R vector is from here to here, the F vector is here, then R cross F is in this direction. And the R cross F takes care of the perpendicular component thing, because only the perpendicular component of the component of F perpendicular R is going to have any effect on the magnitude of R cross F. Anyhow, that's our definition of torque. And we make the statement at 10 centimeters from the axis, we would need 4 times 0.16 newtons, 0.64 newtons for the same effect to get the same acceleration out here. So we say that the force in this case where we're exerting the force at the 40 centimeter position, the 0.16 Newton force at the 40 centimeter position, the torque comes out to be 0.064 meter newtons. If we do 10 centimeters, we have to multiply that by 0.64 newtons. Okay, if R shrinks down by a factor of 4, F has to increase by a factor of 4, and it'll give us the same torque. And that gives us the same effect on angular velocities. In other words, same angular acceleration. Now that's pretty much being asserted right now. We'll see more deeply why that has to be the case. In any case, well, those are the torques, okay? That's how the torque works. We'll go on and talk about energy considerations a little more than what we did over here in the next video.